Hi you guys, so I got a request for Thevenin equivalent circuits and Norton equivalent circuits, so I thought a pretty good problem is problem 63 from chapter 4 on Thevenin and Norton equivalent circuits. And here we have an 80 volt independent voltage source in series with 10 ohm resistor. Then you have a 30 ohm resistor, a 2.5, and some load AB that you're trying to figure out what it's seeing. And I don't know about you, but I think it's pretty profound that no matter how complex a circuit is, that Thevenin and Norton, they said that all you have to do is find what the load that you're looking at sees as far as a current source and a resistance source, and it can be simplified into those two components. That to me is pretty darn profound and pretty cool. But the steps are always the same. When you're looking for the Thevenin equivalent circuit, you always eliminate the voltage or the current source, and you do that. So you get rid. So the first thing, and this is going to be a recurring theme, because if you're struggling with Thevenin and Norton equivalent circuits, then you'll get the steps down and you'll start to memorize there's a flow and a pattern to solving these types of problems. So you get rid of the power source. So if the power source, like in this case, so that means in this case for the voltage source, you're going to open voltages, or if it's a current source, you're going to short the current. Okay, so write that down. If you're struggling with these types of problems, write that down as your step, the first thing that you do in finding, and that is how you find R-Thevenin. That's the first thing you do. After you find R-Thevenin, you're either going to use something from your toolbox to find either the current source here that's going through if you're looking for a Norton equivalent circuit, or you're going to find the voltage right there. Your tools will include source transformation, right? Everything that you've used to date, or most likely your bread and butter is going to be the node voltage or node voltage or the mesh, right? So those are going to be your bread and butter. Your mesh you're going to tend to use for finding I short circuit for Norton equivalent circuits, and your bread and butter pretty much for finding your Thevenin voltage, your V-Thevenin, is going to be node voltage. But you can also always, if the circuit lens itself has dependent sources, you can also of course use superposition if you have multiple voltage sources. I don't like superposition, it's a personal preference thing, but if you do, you can use a superposition, no problem with that. I am a fan of node voltage and mesh current, so I tend to rely on those as my bread and butter, but they don't always work, and sometimes I have to use the dreaded superposition. So always your steps are find R-Thevenin, get rid of the power source. After you're done, restore the circuit to the way it was. Use node voltage or mesh currents to find your V-Thevenin or your I Norton. Okay, let's get started. First, pause the video, try it on your own. Okay, actually do these things, and then if you get stuck, then advance the video to the point that you're stuck and check yourself and continue. Okay, so let's find the Thevenin equivalent circuit. Like I said, the first thing you're going to do, I always do, is find the R-Thevenin. That means we're going to short the circuit. I'm going to draw the new circuit in red for comparison. So to find it, we're going to just draw everything like we did before. I got my 2.5, and what we're doing here is we're finding what is the resistance seen by the load, right? Obviously, this represents the load. It's not. If there's no interest to us in seeing what an open sees, but it's kind of like these are the two eyeballs of a load that you want to attach to some kind of complex circuit. and you want to see how this load will react to the circuit that exists. So here are the eyeballs of the load, A and B. And what does it see as far as the Thevenin resistance? Well, we shorted the load, right? So this is just a piece of wire. So this piece of wire is connected at two ends to that 30 ohms resistor. So that's really 30, this 30 ohm resistor is really in parallel with a 10 ohm, right? So since I left that pre-worked sheet at home, I am going to calculate this here. I have to work out all the problems in advance and then model it in P-Spice and see if I get the right answer before I post it. 1 divided by 10. Okay, inverse that. And I hope that's right. Let's see, let's try again. 130, 1 divided by 30, plus 1 divided by 10. Okay, so this gives me 7.5. That sounds about right, because that's less than 10, right? So I'm going to replace this here with 7.5 because that's equivalent. All right, so this is really just 7.5. And this now becomes what the load sees is, as it looks its eyeballs here, is the 2.5 in series with a 7.5. That's going to be 10 ohms. So your R-Thevenin is 10 ohms. I know this is one of the problems with an answer in the back of the book. It's 10 ohms. So that's my check figure. So now I have one of the numbers that I need for my circuit. R-Thevenin is 10 ohms. Now the next thing we need to do is we need to find V-Thevenin, right? What is the voltage seen by the load here? It's not 10, right? It looks like it would be when you first start. You're like, oh, well, I see 10. But that's not quite true because a voltage drops across this 10 ohm resistor and something happens here. So the only way we can find that is we can use our tools, right? I can use source transformation if I want. It doesn't give me any advantage in this case. And besides, as I already told you, I'm a big fan of node voltage method. So you use whatever you want. I'm going to use node voltage, right? Which is essentially an application of Kirchhoff's current laws at each node. We have two nodes of interest here. This node here, which I'm going to call V sub x, right here. V sub x, right? I don't know what that voltage is, but I'm actually interested in this one, but I have to find that one in order to find this one. V-Thevenin, this is what the load sees at that point. After a certain amount drops here, then we're interested in what does the load see at that point. So, node voltage says the sum of all the currents in and out of the node must equal 0. In other words, current is always conserved. So we have that current plus that current plus that current has to equal 0. So it's an application of KCL, right? Remember, V is equal to I, R, therefore I is equal to V over R. So we're going to take I, which is going to be the difference in voltages, V over R, out of each of these branches to find the branch currents and set up our node voltage equations. So, node voltage at V sub x is going to be Vx minus 80 volts over 10. That's that branch current right here. This branch current, by the way, that's the ground, of course. That branch current is going to be V sub x over 30. This branch current is going to be V sub x minus V-Thevenin over 2.5. All of that has to sum up to 0. Now, I'm going to group things together so that I can put it into my engineering calculator and have them the calculator do the math, which I personally don't care about. V sub x, let's use colors and make things easy to see. V sub x. Group all your coefficients for V sub x into 1. You got a coefficient here, 1/10. None there. I got 130 here. I got 1/2.5 there. That's nothing, right? So I'm done with all my coefficients for V sub x. Now I have a very small whiteboard. Sorry about that. That's going to be, now I need to grab all the coefficients for V sub Thevenin. Holy moly, this whiteboard is too small. So then V-Thevenin, what are my coefficients for that? Coefficients for V-Thevenin are not that, not that, not that, not that, just that. -1/2.5. All that's equal to, now my constants go on the opposite side of the equal sign with a negative, right? Because I would bring that over, -80/10 becomes +8 on this side, right? Yes. So do I have a constant, no constant, no constant, no constant, no constant? So that's my number one equation. This is my number one equation. I have two unknowns, so I need a second equation, which I'm going to get at the V-Thevenin node. Okay, so node voltage at V-Thevenin gives me this branch current, and there's no branch current here because that's an open. So all it gives me is V-Thevenin minus Vx over 2.5 equals 0. Now I'm going to rewrite that with just coefficients to set it up for my calculator. So my second equation for my calculator is grab all the coefficients for V sub x, and the only coefficient that I have is that one, a -2.5, -1/2.5, plus V-Thevenin. My coefficient for the V-Thevenin is just 1/2.5. I have no constants, so it's equal to 0. Now I'm going to enter all that into my scientific calculator. I don't know which kind you have, but you should get to know your simultaneous equation solver pretty soon, because you don't want to be solving it by hand, because that's not electrical engineering. That's accounting. That's not even math. It's accounting, and you don't want to do accounting when you're studying engineering. So get to know your scientific calculator. 1 divided by 10 plus 1 divided by 30 plus 1 divided by 2.5. Enter. Negative 1 divided by 2.5. Enter. Then -1 divided by 2.5. And then 1 divided by 2.5. 0. And then F5 to solve. And I might have made a mistake here. So I have an error in my node voltage equation somewhere. Let's see. And this will happen. So Vx minus 80/10 plus Vx over 30 plus Vx minus Vth over 2.5. So Vx 1/10 plus 130 plus 1/2.5. Oh, I know. Not a mistake in the equation, a mistake in typing in typos. Okay. Calculator typos. Try one more time. Okay. Two equations to do now. 1 divided by 10. equals 8. I forgot to put an 8 there. I'll try again, and for sure. So the calculator tells me that this just happened. This V-Thevenin is 60 volts, and this also happens to be 60 volts. And how can you have 60? It works out. I'm not going to, it seems weird that you have 20 voltage drop here. Oh, of course, so 20 volts dropped here, so that means Vx is 60 volts, and then naturally VTH is in parallel with Vx. Since nothing drops here, since it's in series with that, and it's an open, treated as an open, so naturally you would expect VTH and Vx to be equal to each other since they are in parallel. So now we have all our information. Let's draw our Thevenin equivalent voltage. Write a note here, V-Thevenin is equal to 60 volts. And a Thevenin equivalent voltage is the voltage source, the V-Thevenin, in series with the R-Thevenin. So, alright, so our Thevenin equivalent voltage is and that's your answer. And I don't know about you, but that's pretty cool, in my opinion, that you can attach a load to any circuit that the same circuit that we saw over, and it will behave exactly identically as that. That's pretty darn cool. Anyways, thanks for watching, and I'm going to post this now.